Uh, you're the first group of students that I'm teaching how to use Onshape as part of this course. And I, quite frankly, am really excited about it. I think there's a tremendous amount of potential here. And I think about the many ways that I have taught this course over the years, and the notion that instead of, when you do your calculations, instead of seeing a number or a graph, that you will actually be able to see a design of the finished piece there. I feel like that is just so much more powerful. And so I'm excited about that. So I want to show you a piece of that. So today, fluids review, but first, a little bit about what Onshape can do. So I thought I would begin with just a few views of Onshape so that you can make sure that you understand what it is that we're looking at. And then I'll take you into Onshape for just a little bit of a tour. So this is a preview of a water treatment plant that's designed for, well, where this code can handle flows between about 10 liters per second and 80 liters per second. So by just changing one number, this entire design will change. Unfortunately, I can't just show you that because it takes a couple minutes for it to refresh when you change the flow rate. And so it's not fun to sit there and wait 2 minutes and wait for the design to change, but trust me, it does eventually update. So I would take a guess. This was for a 30 liter per second plant. This would be a plant that would serve something like 10,000 people, perhaps. And the scale, you should be complaining because there's no scale in this image anywhere, but the length here that I'm tracing with my cursor for this tank is, I'm guessing, about 7 meters, okay? To give you a little bit of a sense of scale. And yeah, I tend to go metric the whole time. I know that you know metric and you maybe are more familiar with using English, but this is one of the ironies. I've been always very interested in going metric because it's just so much easier to design things in metric. And then we go and work in countries where, you know, our view is that everyone on the planet uses metric. And then you discover when you walk in that, well, actually, yeah, they use metric, but they also use English, and they also have another set of units that they use locally. And so it gets confusing. And it seems like we managed to pick countries to work in where the English units are still a holdover, both in India and in Honduras. And I've also been connecting a little bit with Guatemala, and the same thing is true there. So you're very much like all the other folks that I'm working with, that the English units are still hanging around. Okay, so we're looking at this plant. We're looking at a top view here, an end view, and then the isometric view. And then let's go in and look at individual pieces. So there's the top view of the plant, and that plant has many subcomponents. So the first one I'll pull out is the entrance tank. And the entrance tank, if we open up the side, it looks like this. So you can see the internals in that tank. The water is entering right here, flowing across the entrance tank, and then exiting through this linear flow orifice meter that we will learn about not too long from now. And then exiting down through this pipe where it then enters into the bottom of the flocculator. So here's the entrance tank, flocculator right next to it. So the next piece is the flocculator. The flocculator, the water has to go up and down, 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 and go through many expansions and contractions and generate lots of turbulence and ultimately generate lots of collisions between particles. From there, it passes into the sedimentation tank. The sedimentation tank, in this case, has, well, that's funny. Here there are 4 bays, and up here there were 5. So if you're counting, you're like, whoops, Monroe got this from 2 different designs. But don't worry, I'm just showing you how this works. And the point is, I can so easily change how many sed tanks or how many units are part of one of these sedimentation tanks by changing the flow rate. So the water enters each of those sedimentation tanks or goes through them in parallel. It goes through in this case, one of these 4. And if we open that up, you can see that there's lots of good stuff happening inside that sedimentation tank. And we'll have a whole set of notes, a whole set of talks about how sedimentation tanks work. And then the last big process is the stacked rapid sand filter. And that is a complicated mess with lots of pipes and hydraulic controls that make it all happen. So you can see inside the filter box, you see that there are tons of pipes inside the filter box. Okay, so we're able to change the flow rate at the very top level and have all of these subcomponents update correctly and redesign themselves with that new flow rate. And I wanted to just illustrate what needs to be happening there. So way up high in our, for the plant design, up on the left-hand upper corner of our screen, and I'll show you where this is at, there's a place where we can enter what we call overrides. And that's where we can enter in the flow rate. And when that flow rate gets entered in, it then is passed through code down to each of the subunits so that they get designed to be the right size as well. So the parent passes the information down to the children, and that notion of parent passing down to children actually happens at multiple levels within our designs. There are a parent who passes down to a child, who has a child, who has a child, and I'm not sure how far that goes, but it at least goes like 4 levels, maybe even further. And all the way down, it's possible to pass down whatever information is needed so that when it all comes back together, it all fits and we have a plant layout that makes sense. So with that, I'm gonna break from that, and I'm going to switch to this. So now you're seeing the plant in 3D, and I can rotate this around, and you can see that there's a lot of stuff going on. There are lots and lots of pipes, and we can take a peek into one of these, just like I did before, where I can hide an element, I think. Okay, and we can look inside a tank and see what's in there, and there's a lot of pieces going on. So that was the entrance tank. We can look down, and in this particular design, I have turned off, up here in my inputs, I've turned off replication. I made replication equal to false, and I did that. Replication equals true would like replicate all of the duplicated parts as many times as are actually needed. So for example, if you look into this tank right now, you'll see that the flocculator, there's only 2 pieces of plastic here making the little baffles, and all the rest of them aren't drawn. That's because I have rep set to false, and I do that so that I can move around here and show you things quickly, because it starts to get slow as we start making all these pieces show up. I want to talk a little bit about how Onshape works. So Onshape, ultimately everything in Onshape is computer code. You can either create drawings directly by writing feature script code, or you can create them using this feature list, which is on the left-hand side of the screen. In either case, it's created using code. And all this feature list is it's a nice graphical representation of a set of functions that are being executed. So remember that execution happens from the top of this left-hand panel down through. And if you want to make it stop prematurely, you can drag this bar, and I'm not going to do it because it takes a long time for this to reload. you can drag that bar back to wherever you want to stop the execution, and it'll stop at that point, and then you can edit it at that point if you like. So execution happens from the top to bottom. This is all just computer code, but with some nice interfaces that make it easy for you to create new objects. And you'll notice here that this is then the code that is used to create this whole plant, which seems like we're cheating, and we are, because you can see very clearly there's some code up here called plant, and then there's the sedimenter, and then there's a flocculator, and then there's a port between the flocculator and the sedimentation tank, and then there's an entrance tank, and then there's a filter. So you can see that pieces of code that are bringing each part in. What's maybe cheating is that each of those pieces of code has a whole lot going on inside it. They're complicated modules. So that was that. And I wanted to point out that, okay, here's where the flow rate is input. If I were to change that, everything would change. If I would type in 30 there, it would redesign this plant for 30 liters per second. Okay, and maybe in the interest of full disclosure, one of the challenges that we have is that we're essentially adding some more capabilities to Onshape than what they were originally intending. And our method of passing information between layers is something that we invented. And it was difficult for us to be able to pass numbers with units between layers. And as you will find out as you work with me, I think it's super important to, when we're designing things, to design using numbers with units, and to have the numbers with units go through our design process. So feature script normally handles units just fine. It's just that we have this little issue of the way we needed to pass information between parent and child. That didn't work out fine to handle units. And so you'll see here that my number 20 doesn't have units on it. And man, this is a little messier than what I was intending to get into today, but the way we handled that is we have code that looks at the variable name, and we have very precise naming conventions for our variables, so that just by looking at the variable, you know what the units have to be. So a variable with the name capital Q in it has to be a flow rate. And then the M after that Q stands for milli. So this is milli flow rate. So the default units for flow rate would be cubic meters per second, because it's just standard SI units. And then a milli of a cubic meter is a liter. So QM gives you liters per second. So I can enter 20 in there, and that gets processed into code as 20 liters per second. Matter of fact, I should be able to come over here, and now I've pulled up the variables that are defined in this code, and there's QM max, and it has a value of 0.02 cubic meters per second. So we processed it. It's got its units attached to it. It's 20 liters per second. There are also, and I'm realizing you're not a computer science group, so I am not sure how to talk about this. There's a map, which is a list of variables that are defined for each subunit. So for example, up here is entrance tank, and here is a list of variables, and that list goes on, and we can't see nearly all of them, but you can see that, for example, here's FB, which is our freeboard of 10 centimeters. There's a length of the entrance tank. There's now another list of variables related to a linear flow orifice meter. So all this information is packed in here, and there's ways to access that if you need it as you're continuing on in the design. And what I'm showing you here, in case you're worried that you're going to have to create this tomorrow for an assignment and it's not going to look good, don't worry. You're not going to be creating anything this complicated over this course, although you will get to play with some of this. We'll work at building this up so that you're comfortable and you're starting with something simpler and you see how it works. Okay, so those are a bunch of variables. And then one more thing that I wanted to show here is that we have a bill of materials. So this bill of materials is the list of all the parts that are in this whole plant, and it includes their prices and the quantities. And I've added this recently. There's also a cost that is the total cost for this project for the materials is $50,000, okay? And then the cost per liter per second is sort of a measure of the efficiency of this design. Like how much does it cost for every liter per second of capacity that this plant can deliver? And you can see here, we calculated it to be basically $2,500 for every liter per second of capacity. Our experience is that by the time you actually build a plant and you include all the labor and all the design work, the costs for building a liter per second of capacity exceed $10,000. So this is a fraction of that, because this is only the material cost, and maybe not, well, this does not yet include all of the material costs because it's still missing a building that goes around this whole plant. There's also a cut list, and I want to just show you that even though we don't have every plate settler drawn in this plant, they all are here. So here's the list of polycarbonate sheets that are 0.5 meter long, and there are 604 of them. So there are actually 604 plate settlers in this plant. Even though they're not all drawn, the software knows about them and has kept track of them. I realize I've just been like brain dump showing you a whole bunch of stuff. Anybody have a question so far about what you're seeing? Don't be shy.
I have a question.
Sorry.
For the vendors and the cost estimates, where do those come from?
Great question. Okay, so we have a database, which at this point starts in a Google Sheet of vendors and prices and the information that we need to actually draw those parts. And what we are doing is we have this set up so that we can have multiple parts in that database that would be used by different implementation partners. So we have parts that would be used by our partner in Honduras. We have parts that would be used by our partner in India. And we have generic parts that would be available here in the United States. And you can, up in this overrides, you can say which partner you want this to be designed for. And then it will pull parts from the database that that partner has access to. Did I answer your question? Okay. There was another question and I don't know who was asking.
I had a question.
Yeah.
For your code on the back end, how does it know where to place all the items? Like place all the features you're making?
So another great question. We use mate connectors on parts to tell us where to bring the next piece in. And there, you might be wondering, like, given that everything can change in dimension, right? And yet even when it changes in dimension, things remain at the right relative positions to each other. And the way that we've done that is by placing the mate connectors on the parts at like in stable locations where it then makes sense to always have the other unit process be attached relative to that location. I feel like I didn't answer that question, but you will play with mate connectors and bringing parts in your next assignment. Yeah. Another piece is that we have the ability to know, like in advance, before we actually start sketching things, we have the ability to know how big things are. And so we can say, oh, this next part has to go 10 meters in this direction, because that's how big a part is. So before we bring a part in, we already know how big it is. Other questions?
I have a question.
Yeah, Finn.
So later on, when we do the design assignments on Onshape, we'll be directly modeling them, not using any sort of code. Is that right?
You will be doing a combination. You will be directly modeling them in that you will not be creating geometry in code. You will be doing hydraulic design in code. So you will be, for example, determining the dimensions of a tank by, like, you figure out what the volume needs to be and what the dimensions need to be. And then once you know the dimensions, you will use that to use a feature that draws a tank, and you will set the dimensions in that feature using the dimensions that you've calculated using variables. Did I answer that?
Yeah, thanks.
Yeah. There's always, Izumi and I are always trying to figure out what are the right times to draw something using feature script, kind of like at the source, and when is it better to use these features that make it easier and more intuitive to use. And we go back and forth. We use features, meaning where you drop a part in and you're not doing it writing the code in feature script as often as possible, because it's easier to see what's happening and to understand what's happening. Any other questions? I'm going to switch back to my presentation, and I know I have to share my screen. That I forgot one other time. PowerPoint slides. That looks promising. Okay. So we did that, and now of reflection, what didn't you see in the plant? And I want to think about this. You didn't see any pumps, right? There were no pumps in all those drawings that I showed you. And there was nothing that looked like this. This is a section from a water treatment plant. And it includes conduits for electrical wires. It includes pneumatic control tubes. Do you guys know what pneumatic control tubes do? Like, how would you? You need a course in automation. So if you want to move a big valve in a water treatment plant, one of the ways of making that big valve open or close is to have a computer that sends a message to close that valve, and that closed valve gets turned into a signal that opens up or closes a little valve that controls air. And then the air goes in a hose, in a tube, up to the actual valve that you want to control, and that air pushes that valve closed or open, whichever way you're going. Okay, so you have software that controls electricity, that controls a little valve, that controls air, that controls a big valve. So in water treatment plants, there are often bundles of these pneumatic control tubes running around the plant to get that automated control. And you didn't see any computers. And that is kind of the motivation for today's class, in that you didn't see all these things. And instead, what we're going to do is we're going to work really, really hard to do all of our controls using hydraulics and like smart fluids. So why are we doing that? It's because computer controlled flows and water levels in water treatment plants cause a lot of problems. They are easier to design, but they're much harder to maintain. They're easier to design because you can just pull existing components off the shelf and say, get this widget from supplier X and put it in this design. But they're much harder to maintain because all of these parts have lots of components that ultimately fail. And here's one of the reasons why I think our design of plants is particularly challenging to think about bringing into the US, where we are extremely risk averse and where making sure that you are not liable to a lawsuit is like what's on everybody's mind. By using other vendors' parts for every piece of the plant, it enables consultants to pass a design risk or a design error risk off to the vendors. So the vendors are responsible for making sure that their parts actually do, what the consultants specify. And so it's not a part that the consultant is designing, like the consultant isn't designing the hydraulics for the flocculator in a certain way to provide the mixing that's necessary. The consultant is putting that design off onto a vendor who provides a mechanized mixer that meets those specifications. It introduces unnecessary complexity, and that complexity ends up getting in the way of successful plant operation because it's more difficult for the operators to diagnose problems. With a complex system like the one I was describing with electricity and air and valves and computer software all working together, there's so many systems built on top of each other. It's difficult to figure out what's wrong when something is wrong. And there's so many parts. So every time you add these mechanized control systems, each of those has many moving parts and many electrical contacts, all of which are susceptible to fail. And to remember, a water treatment plant is actually not a nice place for electronics or moving parts because it's wet, it's damp in a water treatment plant all the time. So for all those reasons, we're interested in doing this as much as possible without using those kinds of parts, or at least creating designs that work well, even if they don't have those controls built in. So we use smart physics and fluids. We attempt to create fail-proof designs using smart hydraulic controls. And hopefully we make it a whole lot easier for operators to learn how their plant works. We eliminate almost all of the moving parts, and we design the geometry so that instead of electrical motors moving things, instead of that, we make the water move. So we create the geometry so the water has to move the way we need it to move so that the right things happen. And then essentially we turn our computer code into concrete and PVC. So or rather our implementation partners help with that process. And the operation of the facility is then controlled by how the plant is actually built and how the plastic components are put inside the concrete tanks. So now all of that is to say, we need to know how fluids work. And I know that almost all of you, or maybe all of you, have taken fluids course at OSU. So this is not questioning that, because I do the same thing in previous classes with other students as well, where I feel like I taught fluids for 10 years. And my reflection from all of that was that it would be better if all students took fluids twice, once to kind of begin to learn how it works and maybe bomb out on a few concepts, and then take it again and more of it would begin to make sense. So I know you didn't, most of you presumably did not have the opportunity to take fluids twice. So we'll talk about fluids for at least today and Tuesday to help refresh your memory and maybe make a few concepts a little clearer for you. So we want to talk about drag, we'll talk about head loss, we'll talk about the Bernoulli and the energy equation when we'll have some fun. And this is where I want you to just be bold, and I'm going to ask you questions, and I want you to vote just to, without any more information, I want you to just vote for what you think is right. And then we'll discuss what we know is actually happening. So what I like bicycling, actually, I like tricycling, but it's easier to think about bicycling. So what causes the majority of air drag on a bicycle, including the rider? Is it pressure drag, shear drag, or lift drag? Okay, so I'll give you something like 30 seconds. Patrick's gonna throw up a poll for you, and just be brave. Don't worry, you're not being tracked on this. Just make a vote. Go ahead and vote. Like it doesn't. I just want like your first thoughts. I guess Patrick is seeing how many votes are in. Are votes in?
19, so a couple more. No, that should be everyone. 'Cause
Excellent.
Some of us don't need to vote, so.
Yeah, a
Right.
few of us.
Can you all see the results?
Excellent. Okay, so first of all, you see that it's split. So you all took fluids, and this question, like it wasn't obvious what the answer is. So it turns out that it's pressure drag. Pressure drag is the big thing that cyclists are getting hit by, and it's about a big wake that is forming behind their body. And that's why the bicyclists try so hard to lean over and reduce the amount of area that they're projecting into the air, because the bigger their body area is that's going forward, the bigger the pressure drag is. Shear drag would be number 2, and then lift drag. I'm sorry, I just made that one up. It was just 2 technical words stuck together, and it doesn't actually mean anything. So I apologize for being mean. Okay, so what did you learn from this? You're just, at this point, you're just like taking Monroe's word for it. Pressure drag is a whole lot more significant for a bicyclist than is shear drag. You have to have a very streamlined body before shear drag ends up being the more important thing. And our human bodies are not very streamlined. Perhaps if you were a dolphin, and I don't actually know the answer for a dolphin, dolphins are extremely streamlined, and it's perhaps, I don't know the answer, you could look this up, whether their drag is mostly, or whether what's slowing them down is mostly fluid pressure drag or shear drag. But for us on a bicycle, it's pressure drag. Okay, next poll. Which orientation causes the most drag? These are all round discs. So just a round disc, maybe with smooth edges. And I'm holding, one of them is flat, one of them is like this. And then 3 and 4, they are hemispheres. So like a cupped hand, okay? And in one case, the cupped hand is like this, and the air is coming from this side. And in the other case, the cupped hand is like this, and the air is coming from this side. Okay? And I want you to think about which do you think will have the most drag. You can assume that the diameters of all these guys are the same. Okay, do we have a quick vote? Don't be shy. Oh, we needed 4 questions, Patrick.
I'll fix it. I'll end it. Yeah.
that would skew the results.
It's not letting me in.
Well, we can do this one impromptu. We can do this by raise of hands. Okay, so, and don't worry, raising hands for number one, just put your Zoom hand up for number one. Okay, Zoom hand up for number two. I've got 1, 2, 3, 4, 5, 6, 7, 8. I've got about 8. Okay. Zoom hand up for number 3. I've got 3. And then Zoom hand up for number 4. I believe I have 9. So actually I got 10. So if we did science by consensus, then you guys got it right. As an entire class, the vote that won was a hemisphere with concave side facing the wind, and that indeed would have the most drag. And then what's not fair is, well, like, Monroe, how are you supposed to think about this? Like, should there be an equation, or like, how can you look at this and just know which one is going to have the most drag? So let's talk about that. So I'm arguing that it's number 4 is the worst case scenario. And let's see why. So in order to understand this, we need to draw the streamlines that begin on the upstream side of the 2 cases that I'll compare. And it'll be clear why these 2 are interesting ones. The next in line is actually number 2. And I think that one had a good number of votes as well. So number 2 is quite bad. Number 4 is even worse. And then, should I put these in order? 4 is worst, 2 is next bad, 3 is next, and 1 is the best, having the lowest drag. Okay, so why? So if we draw the streamlines, our goal is to identify which of these objects produces the largest wake. And the wake is where the streamlines have separated from the body, and there's this turbulent wake. Think of traveling behind a tractor trailer going down the road. You're in that turbulent wake. So let's do some streamlines. So there's one streamline for this first hemisphere. And there's a streamline going into the center for the other hemisphere. And what you see is that this streamline it went into the hemisphere, it came back out of the hemisphere, and it had to do like a 180-degree bend to actually get going in the right direction again. See that? This part right here is what's critical. There was fluid that was coming out of the hemisphere that had to turn around and reverse direction. And you can't just do an instant change in direction. The F equals ma law makes that illegal. So you have to turn around slowly. And so that's what makes this extra little bend out here, and means that the streamline ends up being away from the body where it's separated. So if we would look at the dimensions of the wake, which is all the fluid in between the streamlines that are separated from the body, the wake for this second hemisphere is bigger than the wake for this first hemisphere. Are you on board with that? That makes sense? It's because a streamline can't just take a sharp turn. It has to bend slowly. And then, okay, point number 3 here is which object has the lower pressure in the wake. And drag is caused by there being a low pressure, partially caused by there being a low pressure in the wake. And if the streamlines are bending hard at the point of separation, then the streamlines will be closer together, and that leads to some interesting consequences. So let's do the next slide. So I'm switching geometry here to a flat plate, and we have a flat plate, flows coming at it, and some of the streamlines are going, well, the streamlines are going around the plate, and you can see that there's flow separation. The flow separation, whoops. I have this problem that because I use Onshape a lot, I think that I should be able to zoom around and look at things at different angles just by moving my mouse in any application. And I just tried that in PowerPoint and it didn't work. Okay, so there's separation right at this point on the disk, and these streamlines get close together as they go around the edge of the object. And what happens if streamlines are getting close together? So we're going to take a 0.1 and we're going to compare it with 0.2, and we actually need to move. I should have moved 0.1 up to a different streamline because I need to be on the same streamline. And if we apply, okay, first, we go back. First conclusion, V2 is greater than V1. How do I know that? Because at 0.2, the streamlines are closer together. And so by mass conservation, if the same amount of fluid is traveling in between any two streamlines, so if the streamlines are closer together, that means that the velocity is higher. Are you good with that? The velocity is higher where the streamlines are closer together. So V2 is greater than V1. We're going to apply the Bernoulli equation here between 0.1 and it's funny, I'm seeing this error in my notes. That 0.1 ought to be up on this next streamline because Bernoulli equation has to be applied along a streamline. It doesn't change the conclusion here. So we have this equation from Bernoulli, and if we just change our geometry and say we're looking down on this plate, then 0.1 and 0.2 are both at the same elevation. So Z2 is equal to Z1. And that means, because the only other terms left are the velocity terms, if V2 is greater than V1, then P2 has to be less than P1. Are you fine with that conclusion? Because V2 was big, that means P2 has to be small to make the equation match. So P2 in the streamlines at the point of separation is low. And if you just travel a tiny bit across the streamline into the wake, your pressure is not going to change significantly. And so the pressure in the wake is also low. I don't know if you found that interesting or not, but it's kind of powerful. With very simple logic, we're able to show that the velocity at the point of separation is high, and that because of Bernoulli equation, that means that the pressure is low, and that means that the pressure in the wake is low. And what it tells us is anything that we could have done to make the streamlines further apart at the point of separation would have made the pressure in the wake higher and would have reduced the drag on the object. And there's a whole field of streamlining that is about doing precisely that. The pressure in the recirculation zone in the wake behind the object is relatively uniform because the velocities in that zone are relatively low. It's turbulent, yes, but the velocities are relatively low. And so the pressure is relatively constant across the entire back of this plate. And that's what's causing the majority of the drag. So the reason that the hemisphere that was pointed into the flow is so bad is because the streamlines are even closer together at this point of separation because the streamlines had to deflect even further. And we have a bigger wake. So we have two things that are bad, bigger wake and lower pressure. Okay, enough of that. Any questions on that? Okay. Then let's, and I'll add even a third thing that makes it bad. This is just like for extra credit. There's flow curvature. The streamlines are curved at 0.2. Streamlines are curved. And if a streamline is curved, think hurricane. As you move towards the center of curvature, you move towards lower pressure. That's another, actually, there's a completely different derivation of the Bernoulli equation that allows you to travel perpendicular to streamlines. And it's like the proof that hurricanes have low pressure in the middle. So that is yet a third reason why the pressure in this recirculation zone is low. Okay, so now let's apply it. So now, Patrick, a quiz for 2 or more, not quiz, no points taken off, only fun learning. So I'm going on a vacation. I can't pack all my luggage in my car because I don't know, I'm taking too much stuff with me. So where should I put the luggage for the lowest drag? I can either put it on the roof rack on top of the car, or I can get one of those little bumper or hitch racks and put it on the hitch rack. Where should I put it to get the best fuel mileage? Of course, the real answer is just don't take so much stuff on your vacation, but okay, let's bring them in, can we? At very worst case, you'll be wrong and nothing worse will happen. Can you share the results? There we go. Yes, you guys have learned some fluids. Good work. It is on the hitch behind the car. You know, what's interesting is on the hitch behind the car, you're essentially putting your luggage in the wake. And it's already in the wake. The added drag is minimal. I'm sure there's probably some additional effect, but it's tiny. Whereas putting it on top of the car, not only do you make the streamlines get closer together at the points of separation, but you also make the area of the wake bigger. You increase the size of the wake, and the force of drag is equal to the pressure related to the difference in pressure in the wake times the area of the wake. So you are right. Put it on the hitch behind the car. Thank you. Good job. Okay, three questions, Patrick. Which equation do you use to measure the head loss in a pipe system? So you're going to design a pipe system and you've got to use some equation, and there's a control volume energy equation, there's a Bernoulli equation, and maybe they're actually the same equation. So which one do you vote for? Control volume, Bernoulli, or they're the same? And by the way, on this one, if you mess up, you're in really good company, really good company. This is probably more than a decade ago, but I was looking at the FE exam and the review booklet for the FE exam had it wrong. So let's see. I'm curious to see how you voted. Oh, bring them in, Patrick. Okay, so this is why this part of the discussion is important, because it is very common to not know the difference between these equations. And it turns out they are different equations. And there's only one of them that you can use to design a pipeline. And unfortunately, if we did science by convention or by consensus, it would not go well here. The correct answer is number one. So for the 16% of you who voted for that one, kudos, and let's find out why it's number one. So there's equation, the control volume equation, and it's a mess. It's got, what is it, 9 terms, too many terms for one equation. It includes things like HP, which is the head added by a pump and the head taken out by a turbine. And it does have head loss tucked away there. Then there's the Bernoulli equation, and goodness, if you look at those terms, it's like, what's the difference? They got the same terms in it. So you could justifiably ask, like, why is Monroe like drilling this one? Why does this one matter? Because they are so similar, except that there's some really big differences. So they are not the same equation. So let's talk about this. The assumptions that are needed in order to make it possible to use the Bernoulli equation are that it has to be along a streamline, it has to be frictionless, no lost mechanical energy, it has to be a constant density fluid, and it has to be steady. And the one of those that you really miss on a pipeline is it's not frictionless. Matter of fact, the thing that you were trying to calculate was head loss in the pipeline, which is like how much friction was there. And so the Bernoulli equation says, well, in order to use me, you can't have any friction. So Bernoulli equations don't work in long pipelines. There are places where we can use them inside a pipeline, and I'll try to make that clear before we're done with this. And here we go. Okay, so now we have 2 places where flow is going to go through a change in geometry. In one case, it's a smooth flow contraction, and in the other case, it's an expansion where the pipe gets bigger. And I've asked 2 questions: which flow loses mechanical energy to heat? Or alternately, that's the same as asking, where can you apply the Bernoulli equation to track what's happening as you go through this change in geometry? So what do you think? Which of these 2, and you can in one of them, which of these 2 can you apply the Bernoulli equation and it's completely legit? And you know what? It takes a little bit of time to get the poll out there. I'm tempted to just do this by raising hands so we can do it faster. So who wants to vote for number 1? Don't be shy. I see 1. And Victor, you've had your hand up for a while, so I'm not sure if this is a new hand or an old hand. Okay, so there's 1, 2, 3, 4. I've got, oh, and there's, okay, you can vote. Go for voting in the poll.
I think I've got it figured out now, so we can, the polls are good to go.
Excellent. And just take a second and then let's pull it in. All right. Okay, once again, if we were doing it by by consensus, we got the wrong answer. And hey, you know what? I apologize. I just realized that the two questions I asked were contradictory. So the poll is a wash and Monroe fails this part of the course, okay? We'll have to do it like that. Monroe failed. And so I can't make any sense out of what you said because I don't know which question you were answering. So I'll just proceed with the answer. That's so funny. I worked hard over the last couple of days to revise these notes to make them clearer, and I clearly failed in that one. So which flow loses mechanical energy to heat? That is the flow expansion. Where can you apply the Bernoulli equation? That is the smooth flow contraction. And when you took fluids, I bet you learned that you lose energy when you go through a contraction in a pipe, which is true. But if you go through a gradual contraction, you don't. And it's kind of fun to understand why do you lose energy in a sudden contraction? And hopefully by the time we're done with this, you'll get that. So smooth flow contraction, we can apply the Bernoulli equation. So in that case, mechanical energy is conserved, and it's completely legitimate to use the Bernoulli equation along a streamline. So we can take a point there and a point there. And what that tells us is that as we go from 1 to 2, V2 is higher, elevation is the same, so that must mean that P2 is lower. So the pressure drops as we go from point 1 to point 2. Energy was conserved, we just converted some potential or pressure energy into kinetic energy. In a flow expansion, there's some weird stuff that happens. And the weird stuff is that after the flow exits that first part, it generates all kinds of turbulence because it has high velocity and it's trying to flow into a low velocity zone. And that high velocity means its flow has momentum, it's got inertia, and it doesn't know what to do with it. Okay, it's not actually human thinking about this, but it's like, I need to slow down. What am I going to do with all this inertia? And it starts like turning off to the side and creating eddies and spinning up and creating turbulence. And then that turbulence ends up dissipating a bunch of the energy. So you end up getting something that looks like this. So you have this very chaotic zone. Sorry, it should have been blue because there was blue water in here, but I didn't have I used red dye number 40 to get this image, so it's red. So that you have this turbulence, and that turbulence is dissipating mechanical energy and turning it, kinetic energy and turning it into heat. And that means that we cannot use that equation. Bernoulli equation does not apply for that second case. So some mechanical energy is converted to heat. Okay. And we end at 340. So we keep on going a little bit longer. Make sure that you ding me at like 332. Let's try this one. We'd like to understand how much water comes out of a hole in the side of a bucket or in the bottom of a bucket. So we're going to figure this out using an equation that we're going to derive, that's the orifice equation, but we're going to use Bernoulli because in here, we notice that if there's a contraction of the flow, we can use the Bernoulli to track it. Oh, I want to give this conclusion. When there is a flow contraction, Bernoulli equation can be applied into that flow contraction. Whenever there is a flow expansion, Bernoulli equation cannot be applied. Okay, so if the flow is speeding up, energy, mechanical energy is conserved. if the flow is slowing down, mechanical energy is not going to be conserved. So here we have flow speeding up as it's coming out the side of this tank. And so, and we're going to have a flow contraction. And so we can use the Bernoulli equation between some point on the surface of the tank and some point in the middle of the jet that's coming out. Technically, these have to be on the same streamline, but you can imagine there's a streamline that starts at the surface of the tank and ends up going through this jet. So we're going to use the Bernoulli equation. The Bernoulli equation means that there's no mechanical energy loss. Nothing is being converted to heat. So let's look at this. The pressure on the surface of the tank is 0, so or it's atmospheric pressure. We can use that gauge pressure as our datum, atmospheric pressure as our datum. So P1 is 0. The surface of the tank is barely moving, so V1 is 0. P2 is also atmospheric pressure, very close. And that means that we're just left with, we don't know what the velocity is at V2, but look, we can get it from, if we set Z2 equals 0, that means that V2 is related to that delta H. And so there's a beautiful equation. V is equal to the square root of 2gh, which you probably saw that equation way back in physics sometime in high school. And that's if you drop an object, that's how fast it goes. So same thing applies to water coming out of a hole in the side of a tank, which is kind of cool. It didn't get there in the same path as dropping it, but it ends up with the same amount of energy and the same velocity. And if we zoom in on that orifice, this is what's happening. So I'm now following a streamline that is coming down along the side of the tank and then trying to take the corner and go out through the hole. And just like before, it can't do a 90-degree bend. It has to bend slowly. And the result is that we end up with the jet having a smaller diameter than the hole from which it came. Was that cool? The jet is smaller than the hole. I don't know if you saw that coming, but it's kind of cool. And it's why orifices work the way they work. So we call that contraction from the fact that the streamlines had to bend, a vena contracta. And what we see is that the area of the vena contracta is less than the area of the orifice, and that the ratio is what I'm calling pi VC. So I use the capital letter pi to mean that I made a dimensionless ratio of two things. So a pi is always dimensionless. So this is my dimensionless ratio of these two areas, and it has a value of about 0.6 for an orifice. So we have that equation, and we have the continuity equation that Q is equal to V times A, and we can add those two into the V equals the square root of 2gh, and we can get a nice equation for an orifice that the flow rate is equal to this vena contracta coefficient, about 0.6 times the area of the orifice. That gives us the actual area of the vena contracta times the square root of 2gh, and we're done. And I would say you should either, one of two things, you should either know like how you obtain that equation, because it's pretty straightforward, or you should just know it. It's a simple equation that describes how fast water is going to leak out of that bucket that you drill the hole in the bottom. Questions about orifice equation? Okay. This equation would most easily apply to an orifice that's in a horizontal plane with the tank above it, so that the depth of submergence is constant over the entire orifice. If it's in the vertical plane, then for depth of submergence larger than the diameter of the orifice, that equation works too. So if the orifice is well submerged by more than like 1 diameter, then this equation works reasonably well. And if you want to be fussy about what happens if the orifice is only partially submerged, then there's a lovely link there for an equation. You have to integrate over the area of the actual orifice opening where water is flowing to get the flow rate. And I feel like, yeah, we can go one step further. We just have a little bit of time. So we've talked about drag. We've talked about the hemisphere cupped into the wind as being the awful system with lots of drag. And you're like, why are we talking about hemispheres going through air? This was supposed to be a course about drinking water treatment, and the fluid of interest is water, not air. So point well taken. Happily in fluids, we don't care. It's a fluid, and the physics is the same almost, except that water is not very compressible and air is quite compressible. But the other transition that we're going to make is that, oh, there's these cool similarities between the case of air flowing around an object and the case of water flowing inside a pipe. Yes, they're different, but a lot of the same physics shows up in both cases. So we talked a little bit about drag, about external flows. We didn't talk at all about shear on a solid surface, but indeed that's the skin drag, or the drag that you feel on a flat plate. That's the shear. That's important when you have a streamlined object. And the cool thing is that there's these nice analogy to what's happening inside pipes. So if we go to pipes, we have major losses, which we talk about as friction, and that's the same as shear, because it's also shear on a solid surface and it's shear on the pipe walls. So major loss is about shear on the pipe walls. Minor loss, and by the way, I think that calling them major and minor losses did none of us any good, because major losses can be minor and minor losses can be major, and those words don't actually help us understand what we're talking about. If you want to like correct it in your own mind, whenever we say major losses, you should be thinking about shear, and whenever we talk about minor losses, we should be thinking about the fact that there was a flow expansion inside the pipe, and we're talking about like a pressure drag. The total head loss is the sum of major losses and minor losses. And to be clear, head loss is just a measure of lost mechanical energy represented as lost elevation. So I'm married to Juanita, and she
It seems that Monroe has lost connection, so we'll just give him a second to come back.
I've been caught in much worse